Hello everyone. So today we will talk about the partial derivatives of a multivariable functions. Now the derivatives are a central idea of calculus. So we want to define the idea of derivatives for functions of multiple variables. In order to do that, let's start with a few things from calculus 1. So recall from calculus 1 what derivatives are. So let f be a function of one variable. So we have only one independent variable. So the derivative of f is defined as, so the notation is f prime of x. This is limit h approaching 0, f of x plus h minus f of x over h. Now, what does this mean? So for a small change in x, we are getting a change in the function f. So the rate of change of this function at a certain point gives us the derivative of the function at that point, right? So geometrically, if this is what my function looks like, let's assume this is y equals f of x, and let this be a point A in the domain. So we look at the corresponding point on the curve and we draw a tangent line. Okay, and now the slope of this tangent line is the derivative of f at the point A. Okay, now we want to replicate this idea for functions of multiple variables. Let's see how we can do that. So let f be a function, and we are going to start with two independent variables. So let f be a function of two independent variables, let's say x and y. Now, in this case, the domain is in R2. This is the real plane. And the range is in R, the real value. So instead of getting a curve like before, we are going to get a surface in R3. So let's draw this. So let's assume this is my domain, and correspondingly we get a surface in R3, right? So let's pick a point in the domain. Let's say this is our point AB. And let's try to replicate the idea of derivatives from the previous case. So we have a corresponding point on the surface. So if this is my surface f of xy, this point will be A, B, and f of AB, correct? Now, there's a problem here. Why? Observe this. This is a tangent line to that surface at that point, but also this is a tangent line to the surface at that point. So unlike the previous case, we have multiple tangent lines in multiple directions. We have infinitely many tangent lines. So which one do we take? And this is where we are going to fix two particular directions. So for partial derivatives, we are going to fix the x direction and the y direction. So we will fix two directions. direction of x-axis and direction of y-axis. All right, let's see how the derivatives are defined with respect to x and y. And then we will talk about the geometrical interpretation of these partial derivatives. So the partial derivative, so okay, let me before start with the function. So let f be a function of two independent variables. The partial derivative of f with respect to x is defined by, so let's do it for a general point xy. The notation is f sub x. It's going to be limit h approaching 0. And now we are going to fix the other variable y. So if we are doing the partial derivative with respect to x, we consider the other variable, other independent variable y, we treat it as a constant. So this is going to be x plus h, y stays same, minus f of x over h, right? Similarly, the partial derivative with respect to y is going to be f sub y of xy, limit h approaching 0. Now in this case, we treat x as a constant, so x doesn't change. So y plus h minus f of xy. Oh, I made a small typo there. So it's going to be f of xy. Coming back to this over h. Okay. Now, what does this signify? We'll talk about that, but before, let's talk about some notations. So we can either use f sub x or f sub y like we did for the definitions, or we can use del f del x, or sometimes it's called partial f partial x, or you can do partial f partial y. And if you have the surface represented by the variable z, so if z equals f of xy is a surface, we can also write z sub x and z sub y. Okay? All right, now see what the partial derivatives actually represent. So let's start with the partial derivative with respect to x. So let z equals f of xy be a surface and AB is a point in the domain of f. Let's draw the surface. So this is my x-axis, y-axis, and z-axis. Let's assume this is my surface And for the corresponding point AB in the domain, so for this point AB, we get this point A, B, and f of AB, right? All right, so now we are going to do the partial derivative with respect to x. So we are going to fix y. In this case, we are going to fix y equals b. So what is y equals b? It's a plane in R3 which is parallel to the xz plane, right? So let's draw this plane. Let's use a different color. So this is the plane y equals b. Now it intersects our surface z equals xy in a curve, right? So this is the curve where this plane intersects the surface. So let C1 be the intersection of the plane y equals b and the surface z equals f of xy. Okay, all right. Now let's just see what's happening on this plane. So let's assume this is our plane y equals b, and this is my curve of intersection C1, and this is the point A, B, f of AB. Now we can draw the tangent line for this curve at this point, right? So let this line be the tangent to this curve C1 at the point AB, f of AB. So the partial derivative of f with respect to x at the point AB is the slope of this tangent line, the line that I've drawn in green, to the curve C1, which lies in the plane y equals b. So what we're doing is nothing new. So it's still Calc 1, but instead of doing it on the xy plane, we are doing it on the plane y equals b. Because as soon as the plane y equals b intersects the surface z equals fxy in a curve, we can do the same thing that we did in Calc 1. Now we have a simple curve, C1, and we can draw a tangent line, right? So we have the same idea for the partial derivative with respect to y as well. Let's see what that looks like. So in that case, we are going to fix the plane x equals a. So once again, let's draw the same surface. So we have the same surface as before. Now we are going to draw the plane x equals a. So if this is a, then this is my plane x equals a, and this is going to intersect my surface in this curve, right? Let's call it C2, and we still have the point A, B, f of AB, right? So now C2 is the intersection of x equals a and the surface z equals f of xy, right? So what's happening on the plane x equals a? We have this curve, which is C2. We have the point AB, f of AB, and we can draw the tangent line at that point, right? So the partial derivative of f with respect to y with respect to y at the point AB is the slope of this tangent line to the curve C2 at this point, at AB, f of AB. Right? So similarly, in the previous case, the partial derivative of f with respect to x at AB is the slope of this tangent line to the curve C1 at the point AB, f of AB, right? So that is the geometrical significance of our partial derivatives. Now, let's see how we can compute partial derivatives. Now, before doing that, it might be natural to ask why we only considered these two directions. So initially, I mentioned that for a surface and you take a point on the surface, you can have infinitely many tangent lines, right? But we chose two fixed directions, the directions of the x-axis and the y-axis. Now, you can actually take any directions, and that is the concept of directional derivatives, which we will cover in the future. But right now, for partial derivatives, we are only going to talk about these two particular directions, okay? All right, now let's see how we can compute partial derivatives. So we are going to do exactly what we discussed. If we are finding the partial derivative with respect to x, we will treat y as a constant. If we are finding the partial derivative with respect to y, we will treat x as a constant, right? So let's start with something simple. So if f is xy squared, in that case, f sub x, which is the partial derivative with respect to x, is going to be what? So y is a constant, so y squared is a constant. So we find the derivative of x with respect to x, which is 1, and y squared. So just y squared, right? Now, if we do it with respect to y, so the partial derivative of f with respect to y, we treat x as a constant. So it's going to be x times the derivative of y squared with respect to y, which is just 2y. So 2x. Okay, so that's the simple idea. So now let's take a function which is a little more complicated than this. So let f of xy equals y times sine of x squared plus xy plus y squared. And we want to find the partial derivative with respect to x and with respect to y. So the partial derivative with respect to x, okay, let's start with this. So y is going to be a constant in this case. So y just stays the way it is. Now the derivative of sine, so this is sine of another function, right? So we have to use the chain rule, right? The chain rule. So the derivative of sine is cosine. So cosine of whatever we have inside. And then we multiply that with the derivative of the inside. And remember, we are finding the derivative with respect to x. So derivative of x squared is going to be 2x. Derivative of xy is just going to be y. And derivative of y squared is going to be 0. Right? So we end up with y 2x plus y times cosine of x squared plus xy plus y squared, right? So we used, let me just write this. So we used chain rule here. Okay. All right. Now let's take a look at the derivative with respect to y. So the partial derivative with respect to y. So this was f sub x. So f sub y. Now this is y times sine of a function which includes y, right? So we have product of two functions. So we will have to use the product rule. So it would be derivative of y with respect to y. So 1 times sine of x squared plus xy plus y squared. And then we have the derivative of this whole thing with respect to y. So once again, we use the chain rule. So it's going to be cosine of x squared plus xy plus y squared. And then derivative of the inside, but with respect to y. So x squared is going to give us 0. Then we have y. Then we have, sorry, we have x. Oops. And then 2y. Right? So we have used the chain rule and the product rule. Chain rule and the product rule. So simplifying this, we get sine of x squared plus xy plus y squared plus y times x plus 2y cosine of x squared plus xy plus y squared. Okay, and that is the partial derivative of f with respect to y. I hope this was helpful. Thank you.